What's up, people? I am super excited to show you in this tutorial how you can connect your R to the rich ArcGIS database. In specific, we will be fetching the Landsat 8 data and also some spatial features to create 2D and 3D map of normalized difference vegetation index. So our first step in today's tutorial is to install the package ArcGIS, which will help us to connect to different layers in ArcGIS repo. And thanks, a big shout out to Josiah Perry, who made this possible and created this awesome package. So I'm really looking forward also to updates on this package. Anyways, to install this one, we first of all need to have a package which is called remotes. And we need remotes here because remotes will help us install this package from GitHub. So the GitHub repo for this package is this one, r and then dash arcgis/arcgis. All right. The second argument that you will provide here is that you want to also install the dependency that is necessary for this package. And then once you run this, I do suggest that you also update all the packages that you might also have, but that are also dependencies over this package, so that everything works properly. Now that we have this, we can then define all the packages that we need to install and then load into R. Of course, we will start off with this ArcGIS package. So that's the first one, which we will need for getting access to different databases at ArcGIS. That's the first one. The second one is the tidyverse. From this one, which is also an umbrella package, we'll be using ggplot2, which is used for data visualization. So this is what we're going to be using for visualizing NDVI. Then one of the layers that we'll be using is urban layer, so boundaries of different cities. And for that, we need the asset package in order to, of course, work with these boundaries. Of course, because the NDVI will be getting from Landsat 8, then we'll be working with raster data. Terra is the package in R to not only load raster packages, but also to modify them. Then another package that we'll need here is class_int, which I like to use for creating breaks, and we will be creating this for our legend. And last but not the least, we'll also be turning this 2D NDVI map into a 3D map using a rayshader package. All right, so the next thing to do is to check actually if these libraries are already installed on our system. So what we're going to do is we're going to take this list called libs, and then we're going to go into the row names of already installed packages. Now, if they're not installed, we need to install them, and we need to write here an if-else statement. So if any of these installed libs equals false, in other words, if it's, if they're not installed, we need to then say here install packages. All right, but we don't need all of them. We need libs, and specifically those that are not among this list of installed libs. And the last thing here, of course, that also for these packages, we want to install the dependencies so that everything runs smoothly. The very last step here, now that we installed all the packages that we need, is to then load them into R. And here what we can do, we can apply to this list of libs a library function, which in R is used for loading packages into R. So ArcGIS has some awesome databases like this one here with boundaries for different units such as cities, regions, countries. And the advantage of the package that we install, which is called ArcGIS, is that we're now able to fetch the data using ArcGIS REST API and load it directly into R and then analyze it. So what we're going to do here is get the city boundaries for Agra, and to do that we'll be using here a data set which is called world urban areas. So it's this one. What you can do is either navigate to the end of this page, or you can search it like I did. Now this, it says here that it's a feature server. What it basically means, this is a polygon file, right? So the best way to explore this is to actually click on this link, which is gonna show you now like a small codebook or metadata of this one. It's gonna show you the extent. And then what you can do next is select the layer here. So we're talking about world urban area, so that's the layer. So you click again. And then what you can do here is explore even further what it has. So here you can see the fields that it has, very useful For example, one of them that we will definitely need is the name itself. That's one. And here also shows you the structure of this. Now, if you navigate back to the top of this page, you see this link to a map viewer. This actually allows you to see how your data looks like on a map, right? So if you click on this one, you will be transferred to a map layer. And over here, you will be able to see the polygons of different cities, right? So this is in Europe, the Middle East, and what we're interested actually is Agra. So what we will be getting at here is actually this polygon for Agra. You can get it for a lot of cities, not all of the cities, but a lot of cities across the globe, which makes it very interesting. Basically, it means that you can replicate today's analysis on a lot of other cities. So anyways, we are gonna work on Agra, so we are just gonna transition back here. And then that we are here, we can actually inspect the columns here, column values, by just clicking on this, all right? So this actually opens a small window and tells you here that these are the column names. And what we can do actually back in R is we can filter this one just by taking Agra, right? And that's gonna be way faster also for us to fetch this. So if you go actually now back to this original one, what you just need to do here is simply copy this link. And don't worry, I will also provide the link to this database in the description box of this video. But for now, what you need to do here is simply copy the link that we have here. And then we're gonna go back to R and use this link to fetch the data directly into R, and ArcGIS package is going to help us get this in the SF format. Okay, so we are back in R, and what I did was simply pasted here the link to that database. What we will do next is declare that this is a URL. I'm going to put here 1 because we will also be fetching Landsat 8 data. Then you need to also put double quotation marks around it so that you actually declare it's a string and it can be consumed then in R. The next thing is to open the connection to this database. And to do that, we can simply here say city data. And then over here, what is interesting is we will be using ArcGIS layers. So this is a package that is inside of this ArcGIS, which is umbrella package. So we'll be using this one to fetch the data. But for now, what we want to do here is use the function ArcOpen. This function is going to connect to this remote source, which is ArcGIS. All right. And then here we simply provide this URL 1, and that's the first thing. So this is gonna provide that. The second thing is to get the specific polygon. And in our case, that's the urban area of Agra from this data. So what I'm gonna do here, I'm gonna create the object city SF. And as I said before, the cool thing about ArcGIS layer or layers package here is that it's gonna give you this in SF format. The function for that is called ArcSelect. Now it's called ArcSelect because here you can also write a query to fetch only that small part and then basically accelerate your query. So over here we need to first of all provide the city data object. So this is our connection to the database, all right? The second one is the fields that you want. And as you remember from the database, what we want here is the names field, because the name field has the name of the city that we want. And then the next attribute is a place where you can write the function. So this is a filter function or where that SQL users will recognize. What you need to write here is the following. So name and then equals to, and then single quotation marks because Agra is here a string, and then you provide simply here Agra. That's it. And then the last final step is to here declare the coordinates reference system that you will be using. And we will just gonna go for the WGS84 because from this one, we can then transform to any other. Okay, this is not all in this section. What we'll do, the last one is to define the bounding box here. Very important because the bounding box of Agra will be using to fetch then the Landsat 8 data specifically for that extent. So I'm gonna here define here city box or bounding box, and then using the SF package and its function, which is called stbbox, and passing here city SF, we'll be getting then the bounding box of Agra that we will then use to fetch that raster data from Landsat 8. We are back at yet another ArcGIS database, and this time we're going to fetch one of the gems here, which is the Landsat 8 imagery. And this one is going to help us calculate the NDVI. So the Landsat is the satellite that goes around the globe, and every 16 days it makes one circle around the globe. So it means every 16 days it takes a snapshot of a certain part of the globe. And then it's collected into images, and this is how we actually get different views here. Now, for the purposes of our tutorial, we need here Landsat 8, and the reason why we're using Landsat 8 and not some other ones is this one has the most recent imagery. So over here at this page, and I will be providing, of course, the link here to the data, but over here we need to choose Landsat 8 views. And once we do that, over here you can see a short description of this service. So we are here dealing with a multi-band, so 8-band multispectral scenes at 30-meter resolution. And this one can actually, as it says here, be used for mapping the change of detection of agriculture, soils, vegetation health, waterland features, boundary studies. So it's a very useful imagery, and it's used across these different disciplines. In this specific tutorial, we'll be using it for creating the NDVI map. Now, how do we do that? Well, thanks to this very cool metadata description, the explanation is actually here. So if you navigate to the bottom of this one, you will see the description here of one of the features. So it says here, to calculate this normalized difference vegetation index, or NDVI, you need to use this formula, and this shows you actually what is the band number that you need to use. So it says here, the band 5 is going to be used for red color and band 4 for infrared. And it even gives you the formula, which is super useful. All right, if you navigate down below, you will also see some other things. You can also notice here that there are some fields, but I don't think that at the moment in ArcGIS it's possible to actually filter, which would actually be quite useful given that vegetation is very strong in the summer. So it would be nice to be able to, let's say, get a certain month of the year, or even a day, or some other things. Anyways, for now, what is actually important for us is to navigate back here and then simply to copy the link to this data. So this is what I'm going to be providing in the description box. So we're going to copy this one, and once we copy, we're going to go back into R, and then in R we'll be fetching then this Landsat 8 data. Okay guys, so once again we're back in R, and now we have here pasted the link to the Landsat 8 data. What we need to do is, as we did in the first step, declare it as a URL. I'm going to call it this one URL2, and again put the double quotation marks around it. The next thing, also as we did in the previous step, is simply to create a connection. So using ArcGIS layers and using ArcOpen, we can connect, and then of course defining here URL2, and then we can fetch the raster itself. For that, we'll be using once more ArcGIS layers, but this time we're going to be using a different function. So this one is called ArcRaster. So it's used for image views like this one. And the first argument is simply the connection name. In our case, that's called a Landsat data. Now that we have this, we need to define the bounding box. Luckily for us, we already have the bounding box of Agra. What we need to do in this step is simply take the minimum and maximum longitude and latitude values. So there are going to be here 4 attributes for each of them. So there's going to be xmin, there's going to be xmax, so these are the minimum and maximum longitude values, ymin for minimum latitude values, and ymax for maximum latitude values. Now we can go ahead and put here the CDP box, and then use these double brackets, and then use the same name here, xmin, that we need. So it's simply going to fetch this feature that already exists in this CDP box. Now we just need to repeat this for the rest, and of course replace here accordingly, based of course on the line attribute name. So we're just going to go here and do also for the latitude, so ymin, and also finally the maximum latitude, or ymax. This is not all, because we also need to define the coordinates reference system that we want to use for downloading this. So that attribute is called CRS, and we're gonna go and grab the coordinates reference system that is the same as the one for the Agra extent, which is in the SF format or Agra polygon. So for that, we'll be using this stcrs and then just passing it here cd_sf. Now there are two more arguments, but they're optional, and they're about the fetching a specific size of your raster. So if you run this without specifying, you're going to be getting 400 by 400 pixels, which I think it's a bit small. So I'm going to go here and say that I want a width which is 800 and height which is 800. Now, if you actually experience problems downloading this, or if it returns an error, then please do remove these two lines and just go for the smaller size layer. Okay, so then when we actually run this whole thing, and we can now then inspect the city raster to simply see what actually it is. So I'm just going to pull this up. You can see the output. And as you can see, it's already in the Terra format, because here it's called spat raster. So that's a Terra format. And it says here that we have 800 by 800, exactly what we asked for. The coordinates reference system, it is WGS84, but as you can see here, it's pseudo Mercator. So we will need to correct for this one. And then there are these different names. So I also want to show you what these names are. So I'm just going to run here actually names and then go for the city raster. So names are actually names of the layers or names of the bands here. All right. And we should have 8 bands, but actually we have more of them here. So it says 8 bands, but there are more. What we care about here are bands 2, 3, and 4, because these have these blue, green, and red. But we do, especially for this tutorial, care about the red, which is 4, and 5, which is near infrared. So this is exactly what was provided to us in the previous one, when we were looking at the description of this raster file. So we also had a formula there, which we also copied, and we'll be pasting here so that we can just work on this one. But it's important to understand what we're doing here. So we'll be using this near infrareds and the red bands from this raster file. So I pasted here the formula from the website, and basically what we have here is near infrared minus red divided by near infrared plus red. So this is going to give us the NDVI, and what we need to do here is simply fetch then those bands accordingly. So as we said here, B5 is going to be the 5th band from our file, which is called city raster. So in order to fetch from basically a list, you need to use again this double ones, and then for the B5, which is near infrared, use here 5. And for the B4, you use, again, the city raster, but this time you use the 4th member of the list. Okay, and then we can actually calculate here NDVI using this formula. And once you actually run this, you will get a raster file here, which we can inspect then right away. And as we inspect, we will see the dimensions are retained. The extents and the coordinate reference system is the same, and now we can here see the values, so the minimum and maximum values. So the values actually in the NDVI, they go from 0 to 1, but here we have this one that goes to minus, and we need to correct for that. Also, if we have, for example, here values that are higher than 1, we would also need to correct for that. Luckily for us, there is a function in Terra which is called clamp, which is gonna help us also do that. So let's actually clamp those values, so to say, and create a new object here, then call Terra clamp. And then there are 3 arguments. The first one is the object that you want to modify. So in our case, NDVI. The second one is the lower bound. So we want lower bound to be 0. Currently it's negative, it's sub-0. The third argument is upper. So we want upper to be no higher than 1. As we can see, we are fine there because it is 0.7. And finally, if I want the values to be returned, I need to put here values equals true. So I want actually values to be replaced. Then we can actually, once we do this, once we run this, we can then also see what's going on. So the values have been replaced, and we can just run this one to see. And as you can see, we did also replace Now the minimum value is not anymore sub-zero, it starts from 0, maximum value is still at 0.7, but again, if we had, for example, higher than 1, this would have also been replaced. So it's a very convenient function. As we prepare to create our 2D NDVI map, there are two preparatory steps that we need to take. The first one is to fetch the legend breaks, and the second one is to fetch the color palette that we'll be using. Starting off with breaks, we can create our breaks using a class in package that we loaded at the very beginning, which has a function which is called class intervals, which basically uses your data points and then creates breaks based on natural intervals. So what you need to do here is, first of all, provide an object on which you want to perform this. So in our case, it's called NDVI clamped. And then you need to provide the number of breaks that you want to have. So let's go, for example, for 7. It might provide you actually 8. It really depends on your data points, but we will take this into account. And then the third one is the style that you want to use. So in terms of the style, as you can see, there are many styles here. There is equal, there is pretty, quantile, there is Fisher and Jenks. So more developed one. These are all natural intervals but based on different logics. We'll be using here equal, but you can opt for other ones, such as, for example, quantile, if you want more statistical distribution, or some other ones like, for example, Jenks, which gives the best, I would say, approximation of this natural class intervals. And then the last thing here is to simply fetch the object breaks. Okay, so once we have this, we can define then the colors. For the colors, we'll be using base R colors, which can be accessed through this function called HCL colors. In order to check what are the different palettes that this function has, I will provide a link to the website where you can see that, and also their names that you can then pass to the palette attribute in this function. The first thing is to get the number of colors. Of course, we want this to correspond to the number of breaks. So what I'm going to write here is simply what is the number of members of this breaks list. So length breaks. That's the first one. The second one is to use the palette. So here I went for the green-brown palette. The reason I did that is, first of all, it's a colorblind friendly palette. And the second one is, I think it corresponds with the topic, which is NDVI. It's an index that measures of course, the vegetation levels. And I want to use green here to indicate more vegetation, or higher NDVI, and brown to indicate a lower one. Well, for that one, I will also need to reverse this palette so that the colors reflect that. So I'm here simply writing reverse equals true. Okay, so we are almost ready to create our 2D NDVI map, but before we do that, we need to coerce that raster into data frame so that we can use GeoMaster in ggplot2. So I'm going to go ahead here and create an object NDVI clamped DF to indicate a data frame, and then I'm going to pass this NDVI clamped into a pipe and use as data frame to coerce it, of course. But here I need to specify that my data frame is, of course, going to have the longitude and latitude coordinates denoted here by X and Y, and it's going to have also a third column, which is going to be the value column, in this case NDVI. Now let's actually inspect this one so that you can see how this looks like. So I'm going to first of all just take the first few rows from this NDVI clamped DF. And what you will notice here is actually it inherits the name of one of those rasters. In this case, it inherits the one which is called near infrared. So what we want to do here is rename this third column. And to rename the third column, we basically simply need here to again call names and select here the third column and simply rename it, let's say it can be called value, but it needs to be a string. We can go ahead and finally create our plots. So let's call ggplot2, and then let's add here our first and only layer, so to say. So we're going to be using here GeoMaster for that purpose, and then we're going to be declaring the data. The data is of course going to be this NDVI clamped DF. And because here we have the main aesthetics, which is fill, we also need to define that. And of course the column here is called value, but apart from that we have two more, which is of course the X and the Y coordinates, so that ggplot2 will know what it needs to plot. So that's the first thing. That's the main layer. Then we can go into customization, and one of them, of course, is to customize our legend in terms of the colors and the breaks. And because here we are using continuous scale, we need to use a scale fill gradient or anything on that level. So scale fill gradient. First of all, we can here define the title of our legend, so it can be simply called NDVI. The second one is to define the colors. We already have the colors, so we simply pass them here. For the breaks, we also have the breaks and we pass them here. And then finally, in terms of aesthetics, we also have something which is called labels. This is how they're going to be printed, those legend numbers. And here we should actually round them, and we should round them to 2 decimals. So simply we're going to pass here breaks and round to 2 decimals. Okay, so this is the first customization that we're going to be doing, but in terms of the legend specifically, we can also customize its appearance. And to customize the appearance of the legend, we use guides argument. Now here, what we need to pass is actually that our main aesthetic is the fill attribute. And then we need to use guide color bar because our legend is continuous. So after that, we can simply define the things that we want to show in our legend. First of all, I would like the direction to be horizontal. So direction equals horizontal. So that's the first thing. The second thing is the width and the height of our bars. So if the legend is horizontal, then we want the bars to be a bit wider and we want it to be thinner. So that means that the bar height is going to be quite small. In terms of the units, I'm going to set it to, let's say, 1.5 millimeters. And that's going to be my choice. Of course, you can change this one as you see fit. As I said, the bar width, it's going to be much bigger. So I'm just going to actually copy this and paste. And of course, put here equals to. And then here, I'm going to actually go for 10 centimeters or 100 millimeters. If you think this is too small or too big, again, you can go ahead and simply edit this one. We can also here define the title position of our legend. So simply title position. I would like to position title at the top so that it's clearly visible. But we can also do, for example, title horizontal justification. So if you want to center the legend title, we can use 0.5. We can do the same with the labels. So we can also center the labels. And we can also define, by the way, the label position here, and we can, for example, say that labels should be underneath the legend keys. There are some other things, for example, the number of rows will be 1, of course, because it's a horizontal legend, and of course we want all the legend keys to be next to each other, so by row equals true. Apart from this, we can also define our theme, and because we will be working and passing this to rayshader, we need to use theme minimal. Otherwise, I like to use theme void, but it's not going to be properly rendered at the moment with rayshader, with the current version. So I'm using this theme minimal, and then I'm additionally using theme to specify some other additional things. Now, because I'm using theme minimal, that means I need to manually get rid of these extra details, such as, for example, grid lines. So I need to get rid of access lines, first of all. So access line, I'm going to define here as element blank. So if you want to get rid of some element in the theme, in ggplot2, you simply say or declare here element blank. That's the first thing. The same goes for access titles. So access title X, I also want it to be element blank. And the same thing goes for access title Y. Basically, this is simply getting rid of that X and Y that would show up. Then we also want to get rid of the text here. So any text on the axis, and I'm simply gonna paste it here, and then just change here instead of title, just put text. Then after we got rid of these excess things such as grids, we can then specify something. And one of them is, for example, legend position. So this is different from a direction because here we put where the legend is going to be. So we're going to put legend at the top. That's one thing. You can, of course, change this. Then we can also, for example, specify legend title. Now, a very important thing here to remember is that legend titles, legend text, other titles, that is all text, and you need to actually tell ggplot to it's text, and for that purpose you're using here element underscore text. All right, and once you do that, you need to open the brackets, and within those brackets you can then specify what you need. So for example, for the legend title, we can specify size, let's say 11 pixels. We can also specify, for example, color. We can go for charcoal gray or something similar. And as we specify this, we can also define other text elements that exist. And one of them is, of course, legend text or legend labels. And we can go ahead and do the same for legend labels. We can maybe choose a bit smaller pixel size. Of course, because here we were getting rid of some of the things, there are also things such as, for example, panel border or plot background, and we need to also get rid of these because we use thin minimal. So what we're going to do is simply go here and define them. So panel grid minor, we need to also get rid of this one, and we need to get rid of panel grid major as well. So these are again those lines that are formed based, of course, on the graticular. So these are some of the things. There's also, for example, plots background. We also want to define that one. We actually want to get rid of that one. So plot backgrounds, it's again going to be element blank. But for the legend title, because legend is going to be actually exposed to the light later on in rayshader, we want the legend background to have a certain color. And because legend background is a rectangular form, we also need to tell here ggplot2 that legend background has a different one. So legend background element rect, as we said, we're going to fill it with the white color. But the color itself of the borders, it's not going to be there. So we're going to simply put here NA or not available. Okay, so these are some of the things that we defined here, that we specified here. I think the one last thing that is, I would say, optional are the margins. So plot margin. We use this so many previous tutorials, and I always find it very convenient. Because you can basically shrink that white space around your plot. That's why I'm using here. And once more, we need to specify 4 arguments here. So for the top side, I'm going to give it a bit more space because after all, this is where our legend and legend title are going to be. But everything else I'm going to shrink. So I'm going to shrink the right-hand side. I'm going to shrink the bottom-hand side, and the left-hand side. I'm also going to shrink and put here -1. So if you're not familiar with this one, shrinking is done if you provide here a sub-zero value. And then importantly, you need to also define here what is going to be your unit. Okay, so once you print that last plot that we created, you should be able to see the NDVI map for Agra, and in this now step we'll be creating a 3D map using that ggplot object that we previously created. So the first thing will be to define the width and the height of our plot, and of course here we'll be accessing that NDVI clamped raster. So the number of columns is going to give us the width measure, and the number of rows is going to give us the height measure, denoted here by h. So once we are done with that, we go ahead and from rayshader, we grab a function which is called plotgg. This function allows you to create a scene and then render it later on from a ggplot object. So our ggplot object is called p, and then here for the width and the height, you will be actually using inches. So what is important here is our width and our height, if we actually run this, they are going to be 800 by 800. So you cannot pass this as inches, it's too big. The maximum is 50 inches, but what you can do is you can divide them, but let's say 100. 8 inches is totally fine. So we can go here for 8 inches, both for the width and the height, and that is very important. So if you are dividing here your width with 100 as I'm doing, you should also divide it by the same number for the height. Okay, so apart from this, you can also define the window size. I mean, the window size is already pretty small, so it's 800. What we can do is simply use that. So we can pass here width followed by height. So it's going to be 800 by 800 pixels. So that's going to be the size of the window. This is possible. Again, it's possible to make it smaller or make it bigger. So you can simply either multiply or divide by a certain coefficient. Of course, there are other things that you can do here. And one of them, how big are those spikes are going to be? So here the default is, so the scale is the attribute that does that. The default is 150, but actually we're going to increase this to 300 because anyways, the scale that we have is pretty small. And also the distance between these different data points and breaks is also not that big. So we're just going to use this 300. And then here, what we're going to also do, we're going to get rid of any a shadow over the panel. So we don't want a panel around our plot, but we do want the shadow itself. So we want the shadow to appear in the plot, and we also want the shadow color to be white. So that's very important for us. Means like we want the shadow to be as weak as possible, and also in terms of the shadow width, we want the shadow width to also be very, very small, so to be basically 0. And finally, we can also define here shadow intensity 1, which means a very weak shadow in the background. We don't want a shadow to actually dominate our map. And then a few last ones are pretty much optional, but they also shape the way your scene looks like. And one of them is the zoom, how much you're going to zoom. I'm just going to go here for 0.5 because this one goes from 0 to 1. 1 is completely zoomed out and 0 is completely zoomed in, so somewhere in the middle. And then here for the degree angle, I'm actually going to go for 85 degrees, so it's going to be almost a normal degree. You can of course play with this one and see what works with you. And the final one that you can also play with is called theta. This is basically how tilted is your map going to be. I'm just going to put here 0 degrees, so it's not going to be tilted. All right, so once you actually run this whole chunk, you should be able to see the scene that looks something like this. If you're not happy how your scene looks like in terms of the zoom level or in terms of the degree and you want to experiment even more, rayshader has a very convenient function here, which is called render camera. A render camera basically, as the name suggests, helps you actually create a different view of your camera. So here you can change 3 values. You can, for example, change this degree level. You can increase it, you can decrease it, you can change the zoom level, and you can also change this theta value, so you can experiment. All right, I'm actually pretty happy how this turned out, so I'm gonna go to the last stage, which is going to be rendering the object. All right, we are ready to render the object, and over here I provided a link to one of the lights, HDR lights that I used in previous tutorials, and we'll be using it once again. So if you don't have it, download it in your folder. We are gonna do it right now, don't worry about it. So first of all, let's define this URL, which I'm also gonna provide in the description box of this video, so don't worry about that. Then I'm gonna actually fetch the file name of this HDRI file. So it's gonna be basically the base name of this U object that I just defined. And then the last thing is to download this file. So to download, we can use download file to base R. We need to provide here URL, which is this U object. Then we need to provide the destination file name, which is going to be this HTML file, so the base name of the file. And then the third one is going to be the binary mode of downloading this light. So finally, we can render the object using a rayshader and the function which is called render high quality, which you use so many other times. The first argument here is the file name, so we can simply call agra here, agra NDVI dash, for example, 3D, so that we don't have the same name as the 2D map. Over here, we can specify that we want to also preview the rendering object as it renders. And here we can also say that, of course, we're going to use the light and we're going to use the special environment light. So the environment light we'll be using is this HDRI file, which is now downloaded to our working directory. So you will be able to access it in rayshader using simply this object. So that's the first one. Then you can also specify here the intensity environment. So intensity of this light. You can increase it or decrease it. I would say that the value of 1 is some kind of a middle. Of course, it depends how rugged is your object, but I would go for 85, which is going to be a bit lower, simply not to have too strong light. And then you can also choose, for example, to rotate this environment. I would like to rotate it by 90 degrees, which means that the shadow will appear somewhere in the southeast of our object. I'm going to turn off the interactive mode, as I always do, because I don't want the scene to crash. And I would like to utilize my resources here. So I'm going to simply call here parallel equals true. I always forget here to actually write the whole ones, not just T and F, which I know that sometimes leads to errors. So I'm going to actually fix this very quick. And finally, what you can do is also define here the width and the height. If you really want to go, you can go for the width, which we define, which is 800. But I would probably want to increase the resolution of the final image, so you can simply, do, for example, times 3. So this is going to be 800 times 3, so 2.4K pixels width. And you can do the same, or actually you should do the same for the height. If you are multiplying width, you should also multiply the height with the same number. Okay, so this is gonna take some time to render, as you probably noticed if you follow some of my previous tutorials, despite the fact that this is actually quite small. But once you run this, you will be able to see a 3D NDVI map, which now gives you a bit more perspective. Where are the areas? So those rugged areas, those spiked areas will be those that have a higher NDVI, and those lower ones, brown ones, those are going to be those that have a lower NDVI. And that's all for today, folks. If you're interested in replicating today's analysis, I prepared the link to the repo in the description box below. Feel free to clone it, reuse it, modify it as you see fit. I'm also looking forward to your own projects and how you take this to some other cities around the globe. If you have any questions, comments, or just general feedback, feel free to reach out to me here on YouTube, but also on Instagram and X. If you're new to R and you seek to expand your data visualization and geospatial knowledge with R, I prepared a few cool tutorials for you, so do check them out. See you next time.